Welcome everyone. I'm excited to kick off our presentation today. We'll be exploring atmosphere and Earth materials with a focus on energy interaction. In this session, we'll cover how the atmosphere interacts with Earth materials and the role energy plays in these processes. So, stay with me as we dive into these fascinating topics. Let's get started. Let's talk about interactions with the atmosphere, starting with absorption. Absorption is a process where molecules in the atmosphere take in energy at different wavelengths. This is a key mechanism because it influences how much radiation from the sun reaches the Earth's surface. Now, the main players here are ozone, carbon dioxide, and water vapor. These are the primary atmospheric constituents responsible for absorbing radiation, and they play a crucial role in shaping our climate and weather patterns. Before sunlight even hits the ground, it has to pass through a certain thickness of the Earth's atmosphere. During this journey, particles and gases can influence the incoming radiation. Two main processes are at work here: scattering and absorption. Let's focus on scattering for a moment. Scattering happens when particles or large gas molecules in the atmosphere interact with electromagnetic radiation, causing it to be redirected from its original path. Think of it like light bouncing off particles in the air, which can affect everything from how the sky looks to how much sunlight actually reaches us. Understanding these interactions helps us grasp how the atmosphere filters and modifies solar energy, which ties directly into our overall theme of how Earth's climate and environment are affected by atmospheric processes. Let's talk about scattering. Scattering is essentially the process where small particles, suspended in a medium with a different index of refraction, diffuse a portion of the incident radiation in all directions. Think of it as light or radio waves hitting tiny particles and then spreading out in every direction. An important point here is that with scattering, there's no energy transformation happening. The energy isn't lost or converted into something else. Instead, it just changes how it's distributed in space. So the energy remains the same, but its position or direction changes. This process, along with absorption, is a key reason why we encounter attenuation issues with radar and other measuring devices. When signals scatter or get absorbed, the received signal becomes weaker or distorted, which can impact the accuracy and reliability of measurements. Understanding scattering helps us better grasp how electromagnetic waves interact with different environments, which is crucial for improving radar performance and other remote sensing technologies. Let's take a look at the different types of scattering that occur in the atmosphere. First up is Rayleigh scattering. This type happens when the particles involved are much smaller than the wavelength of light, like molecules of nitrogen and oxygen. It's responsible for the blue color of the sky because it scatters shorter wavelengths more effectively. Next, we have Mie scattering, which involves larger particles such as water droplets and aerosols. Unlike Rayleigh, Mie scattering doesn't favor shorter wavelengths, so it tends to scatter all visible wavelengths more equally, leading to phenomena like haze and clouds. Finally, there's non-selective scattering. This occurs with particles that are much larger than the wavelength of light, such as large water droplets or dust particles. It scatters all wavelengths roughly equally, which is why clouds appear white. Understanding these different scattering types helps us grasp how light interacts with our atmosphere, affecting everything from weather to visibility and even remote sensing. Rayleigh scattering is caused by particles that are smaller in size than the wavelengths of radiation we're dealing with. This type of scattering primarily occurs from atmospheric gases, which are tiny enough to cause this effect. What's really interesting is that this scattering is wavelength dependent, meaning the amount of scattering we experience changes depending on the wavelength of light. Specifically, as the wavelength decreases, the scattering increases dramatically. It's proportional to the fourth power of the wavelength. So, shorter wavelengths scatter much more than longer ones. This is the key reason why the sky appears blue to us during the day. The blue light, which has a shorter wavelength, gets scattered more widely across the sky. And in the context of our overall discussion about atmospheric phenomena, Rayleigh scattering is the dominant scattering mechanism in the upper atmosphere. It plays a crucial role in shaping what we see when we look up, influencing everything from sky color to the clarity of atmospheric observations. Today, let's explore how Rayleigh scattering affects the colors we see at sunrise and sunset. When the sun is near the horizon, its rays have to pass through a much longer stretch of Earth's atmosphere compared to midday. This longer path means the atmosphere has more opportunity to scatter and absorb the shorter wavelengths, like blue and violet. As a result, these colors are scattered out of our line of sight. What we're left with are the longer wavelengths, orange and red, that are less scattered and can reach our eyes more directly. That's why sunsets and sunrises often appear so beautifully warm and reddish. This process highlights how the Earth's atmosphere interacts with sunlight, influencing the colors we observe and connecting to the broader theme of how atmospheric conditions shape our visual experience of the sky. Rayleigh scattering is a key factor in creating haze in images. When light interacts with tiny particles in the atmosphere, it scatters, and this scattering is what causes that hazy appearance. Visually, you'll notice that haze reduces the crispness or contrast of a photo, making details less sharp. In color photography, especially when taking pictures from high altitudes, this scattering often gives the image a bluish-gray cast. It's that subtle, often unavoidable discoloration caused by the atmosphere's effect on the light reaching the camera. The good news is, we can often reduce or even eliminate this haze effect. One common method is to use a filter placed in front of the camera lens. Specifically, a filter that blocks short wavelengths, meaning blue and violet light, can help minimize the bluish cast and improve the image clarity. So, understanding Rayleigh scattering helps us better grasp why images sometimes look hazy and how we can use filters to get clearer, more contrast-rich photographs. It ties into the overall theme of understanding atmospheric effects on imagery and how to manage them for better visual results. Let's take a closer look at my scattering. This type of scattering occurs when the particles causing it are roughly equal in size to the wavelength of the light passing through. In other words, the particles are just the right size to interact strongly with the light waves. You'll often find my scattering happening due to particles like pollen, dust, smoke, and water droplets. Basically, many of the particles present in the lower atmosphere. These particles can significantly influence how we perceive the sky's color and clarity. Understanding my scattering helps us grasp how different atmospheric conditions affect visibility and the appearance of the sky, tying into the broader theme of how particles and light interact in our environment. Non-selective scattering happens in the lower part of the atmosphere, where particles like water droplets and large dust particles are much bigger than the incoming radiation. Because these particles are so large, they scatter all wavelengths of light roughly equally. This is why fog and clouds look white to our eyes, since red, green, and blue light are scattered about the same way. Recognizing this type of scattering helps us understand how different atmospheric phenomena appear and ties into the broader theme of how light interacts with particles in our environment. When incident radiant energy encounters a substance, it can be absorbed, meaning the energy is retained by that material. This absorption isn't just a simple process. It depends on the nature of the medium doing the absorbing. Different materials will absorb energy differently, transforming it based on their unique properties. However, it's important to remember that the medium won't absorb all of the energy that hits it. Some of that energy will be reflected back, some will bend or change direction through refraction, and others will scatter in various directions. This interplay determines how much energy gets absorbed versus how much gets reflected or transmitted. Different gases and particles in the atmosphere absorb and transmit various wavelengths of electromagnetic radiation. This means that not all wavelengths make it through the atmosphere equally. Some are absorbed more than others depending on the medium. The wavelengths that do pass through the atmosphere without being absorbed are known as the atmospheric windows. These are critical because they allow certain wavelengths, including visible light, to reach the Earth's surface, playing a key role in climate and weather processes. Understanding absorption and these atmospheric windows helps us grasp how energy moves through our atmosphere and impacts our environment. When we talk about the atmosphere, it has certain regions known as atmospheric windows. These are the relatively transparent wavelength regions where the atmosphere doesn't absorb much radiation. This transparency is crucial because it allows us to observe the Earth more effectively in those specific wavelengths. However, atmospheric absorption does pose some challenges. It reduces the number of spectral regions available for us to work with, which means our options for remote sensing are somewhat limited. This directly impacts how we select and design sensors. We need to focus on those atmospheric windows to maximize the quality and usefulness of our observations. So, understanding where these transparent regions are helps us optimize our imaging and sensing strategies, ensuring we get the clearest, most accurate data from our instruments. Let's talk about interactions with Earth's features. In our study of RS and GIS, understanding how these technologies relate to Earth's natural features is fundamental. When we analyze satellite images or GIS data, we're essentially examining various landforms, water bodies, vegetation, and other physical features. These interactions help us interpret how Earth's surface changes over time, whether through natural processes or human activity. For example, identifying deforestation, urban expansion, or water pollution all involve observing how these features evolve. Recognizing these interactions is key to making informed decisions in environmental management, urban planning, and disaster response. So, in our broader discussion, this slide emphasizes how vital it is to understand the dynamic relationship between technological tools and Earth's physical features to better interpret and manage our planet. Now, let's talk about the target interactions in remote sensing. When we're measuring radiation, our main focus is on the light that is reflected from targets on the Earth's surface. One key process is absorption, which we denote as A. This happens when the radiation's energy is taken in by the target itself. Think of it as the target soaking up some of the energy. Then there's transmission, or T, which occurs when radiation passes through a target without being absorbed. Imagine the radiation sneaking right through an object, like sunlight passing through thin clouds or transparent materials. Finally, we have reflection. Labeled as R, reflection is when the radiation hits the target and bounces off, redirecting in a different direction. This bouncing or redirection is crucial because it's often what sensors detect and analyze. Understanding these interactions, absorption, transmission, and reflection, is fundamental because they determine what information our sensors receive about the target. They help us interpret the data accurately and connect to the bigger picture of how remote sensing allows us to analyze Earth's surface. Today, I want to talk about transmission. Transmission is essentially the process by which radiation travels through a medium. Think of it as the way energy moves from one point to another, passing through a material. When we measure how much radiation gets through, we use a concept called transmittance. This is the ratio of the transmitted radiation to the total radiation that initially hits the medium. So, if a lot of radiation gets through, the transmittance is high. If little gets through, it's low. Understanding transmission helps us grasp how different materials interact with radiation, which is critical in fields like remote sensing, optical systems, and environmental monitoring. It's a fundamental concept that connects to the overall theme of how radiation interacts with various media and how we can quantify that interaction. Let's talk about reflection. Reflection is essentially the process where a surface with a discontinuity, like a mirror or water, turns back some of the incident radiation, sending it back into the medium through which it arrived. Think of it as a kind of bounce back. Now, this process is really important because, on average, about 1/3 of the sunlight that reaches Earth gets reflected away. That's a significant portion. If reflection didn't happen, much of the world around us would appear invisible because we rely on reflected light to see objects that don't emit their own light. For example, if an object can't produce its own light, it becomes visible to us only because it reflects light from other sources, like the sun. So, understanding reflection not only helps us grasp how we perceive objects around us, but also ties into the broader theme of how light interacts with surfaces and materials. It's a fundamental concept that influences everything from climate models to how we see and interpret our environment. All right, let's talk about the types of reflection. There are two main types, and which one occurs really depends on the surface roughness of the object we're dealing with. The first type is specular reflection. This is the kind of reflection you see on smooth, shiny surfaces like mirrors or calm water. It produces a clear and defined reflection, where the angle of incidence equals the angle of reflection. The second type is diffuse reflection, which happens on rough or matte surfaces like painted walls or paper. Instead of a clear image, the light is scattered in many directions, which is why these surfaces don't produce a sharp reflection. Understanding these two types helps us grasp how light interacts with different surfaces, which is fundamental in fields like optics and computer graphics. So, whether a surface reflects light directly or scatters it broadly, it all comes down to the surface's roughness and how it affects the way we perceive reflections. Let's take a closer look at specular reflection. This occurs on smooth surfaces, where light bounces off in a very predictable way. When light hits a smooth surface, it reflects at equal angles on both sides of the normal, which is the imaginary line perpendicular to the surface at the point of contact. This means that on flat surfaces, you'll see mirror-like reflections, where images are clearly reflected. A key point here is that the incident angle, which is the angle at which the light hits the surface, is exactly equal to the reflected angle. Understanding this helps us see why reflections on smooth surfaces are so clear and predictable. It's a fundamental concept that ties into how we perceive reflections and how different surfaces affect light behavior in our environment. Let's talk about diffuse reflection. It still follows the basic rule of reflecting off of equal angles, which means the angle of incidence equals the angle of reflection. However, what's different now is that the plane of reflection has changed. Instead of reflecting off a smooth, mirror-like surface, we're dealing with surfaces that are rough or uneven. This causes the light to scatter in many different directions, rather than bouncing straight back. This concept is important because it helps us understand how light interacts with various surfaces in our environment. It connects to the overall theme of how reflection behaves not just in ideal conditions, but in real-world scenarios where surfaces are often imperfect. So, in essence, while the fundamental rule stays the same, the way the light disperses changes depending on the surface's texture. Let's talk about spectral reflectance. This is essentially the portion of incident radiation that a non-transparent surface reflects back. It's important because it varies depending on the surface feature and the specific wavelength of the light. So, the amount of energy reflected at one wavelength can be quite different from that at another. This means that two features which look quite similar in one part of the spectrum might actually be very different when you look at a different wavelength. Recognizing these differences is key in remote sensing and spectral analysis because it helps us distinguish between features that might otherwise appear alike. Overall, understanding spectral reflectance allows us to interpret and analyze surface characteristics more accurately across the entire spectrum. Let's talk about spectral signatures. A spectral signature is essentially a unique reflectance value that you can find in a specific part of the spectrum. What this means is that for any material, whether it's vegetation, soil, or water, the way it interacts with sunlight varies across different wavelengths. This variation is reflected in how much solar radiation the material reflects, absorbs, transmits, or even emits, and importantly, this changes depending on the wavelength you're looking at. When we plot these amounts, usually expressed as a percentage, across a range of wavelengths, the points connect to form a curve. This curve is what we call the material's spectral signature, or spectral response curve. Understanding these signatures is crucial because they help us identify and differentiate materials based on their unique spectral responses. This concept ties into the broader theme of remote sensing, where analyzing spectral signatures allows us to interpret what's on the Earth's surface more accurately. Let's take a closer look at the spectral signature. When we talk about spectral signatures, we're referring to the unique pattern of reflected or emitted energy that an object produces across different wavelengths. Think of it as a kind of fingerprint for materials. Each material, whether it's a type of vegetation, mineral, or man-made object, has a distinctive spectral signature. This uniqueness allows us to identify and differentiate between them from remote sensing data. Understanding these signatures is crucial because it forms the basis for many applications, like land cover classification or mineral exploration. Essentially, by analyzing the spectral signature, we can gain detailed insights into the composition and characteristics of the Earth's surface, which ties back to our overall goal of improving how we interpret and utilize remote sensing data. Let's talk about short-wave infrared, or short-wave IR. This part of the infrared spectrum typically covers wavelengths from about 1.4 to 3 micrometers. What makes short-wave IR particularly interesting is its ability to detect subtle differences in materials and surfaces. It's often used in applications like remote sensing, environmental monitoring, and even in some military and security systems. Because shortwave IR can penetrate atmospheric particles better than visible light, it allows us to see through some obscurants like fog or smoke, which is incredibly useful in certain scenarios. So, understanding how shortwave IR interacts with different materials helps us develop more effective sensors and imaging technologies, tying back to our overall goal of improving detection and analysis methods. Let's delve into the concept of energy interaction. First, this interaction depends heavily on the materials or features we're examining. The proportions of reflected, transmitted, and absorbed energy, denoted as R, T, and vary depending on the specific Earth feature. This variation helps us distinguish between different features based on their unique energy signatures. Second, energy interaction is also wavelength dependent. That means R, T, and values change at different wavelengths for a given feature. In other words, two different features might behave quite differently when we look at them across various wavelengths. Understanding these two key points, the dependency on material features and wavelength, is crucial. It allows us to interpret remote sensing data accurately and helps us differentiate between different Earth surface features based on their energy interaction characteristics. Let's talk about material dependency. This concept is crucial because it highlights how much a system relies on specific materials to function properly. When a system is highly dependent on particular materials, any disruption in their supply can cause significant issues. It's like putting all your eggs in one basket. If that basket drops, everything is at risk. This dependency can affect everything from production costs to the stability of the supply chain. Understanding material dependency helps us identify potential vulnerabilities and plan for more resilient systems. It ties into the overall theme of efficiency and risk management, reminding us that diversifying materials or sources can mitigate these risks. So, in designing sustainable and robust systems, managing material dependency is a key piece of the puzzle. Let's take a closer look at wavelength dependency. As you can see, different wavelengths reveal different information. In the infrared wavelength range, for example, we notice that coniferous trees tend to appear darker compared to other types of vegetation. This darker tone in IR is actually quite significant. It helps us distinguish conifers from broadleaf trees because they reflect infrared radiation differently. Moving to the visible wavelength, our eyes perceive these differences more subtly, but infrared imaging can uncover details that are not visible to us. This variation in how different wavelengths interact with plant materials is a key concept, especially when analyzing vegetation health or type. So, understanding wavelength dependency allows us to interpret remote sensing data more accurately and connect the spectral information to real-world characteristics of the landscape. It's a powerful tool in our overall analysis and helps us make more informed decisions based on what the data reveals. Let's talk about the interaction between vegetation and electromagnetic radiation. First, we see that chlorophyll absorbs light primarily in the 0.43 and 0.66 micrometer ranges. These correspond to the blue and red regions of the spectrum, which are crucial for photosynthesis. Chlorophyll B, on the other hand, absorbs slightly different wavelengths. around 0.45 and 0.65 micrometers, complementing chlorophyll to maximize light absorption. Beyond chlorophyll, pigments like beta-carotene and xanthophyll come into play. These pigments mainly absorb in the blue and green wavelengths, adding to the plant's ability to utilize different parts of the spectrum. Together, chlorophyll A, chlorophyll B, beta-carotene, and xanthophyll influence how vegetation interacts with electromagnetic radiation, affecting absorption and reflection. A key point here is that chlorophyll is responsible for absorbing most of the red and blue light, which fuels photosynthesis. Interestingly, it reflects green wavelengths, which is why plants appear green to us. This reflection and absorption pattern are essential not only for plant health, but also for remote sensing applications, as they help us identify vegetation and assess its condition from a distance. So, understanding these interactions is fundamental in studying vegetation's role in Earth's energy balance and how we can monitor plant health through spectral data. Interaction with vegetation is a key factor that influences each interval of the curve we're examining. Essentially, as we look at different phases, the presence and behavior of vegetation become the dominant forces shaping the outcomes. This means that the way plants grow, interact, and respond to their environment directly impacts the phenomena we're studying. Recognizing this helps us understand why vegetation plays such a critical role in these processes. It ties back to our overall theme by highlighting how biological factors, like plant interactions, can drive large-scale environmental patterns and changes. So, paying attention to this interaction allows us to better predict and manage the dynamics we're observing across different intervals. Today, I want to focus on leaf structure, which is a fundamental aspect of plant anatomy and crucial for understanding how plants carry out photosynthesis. As you can see, leaves are designed with several key parts, each playing an important role. The broad, flat surface of the leaf maximizes light absorption, which is essential for photosynthesis. The upper and lower epidermis provides a protective layer, shielding the internal tissues from damage and water loss. Just beneath the upper epidermis, you'll find the palisade mesophyll, packed with chloroplasts, where most of the photosynthesis happens. The spongy mesophyll, with its air spaces, facilitates gas exchange, allowing carbon dioxide in and oxygen out. The veins, or vascular tissue, are like the plant's transportation system, carrying water from the roots and distributing sugars produced during photosynthesis. Understanding these structures helps us see how each part contributes to the plant's overall ability to produce energy and grow. This interconnected design is a perfect example of nature's efficiency, linking back to our broader theme of plant adaptations and survival strategies. Let's take a closer look at the leaf structure. First, we have the palisade parenchyma. This layer consists of tightly packed, column-shaped cells that are rich in chloroplasts, making it the main site for photosynthesis. These cells are positioned just under the upper epidermis, maximizing light absorption. Next, we come to the spongy parenchyma, which is made up of more loosely arranged cells with air spaces between them. This arrangement facilitates gas exchange, allowing carbon dioxide to reach the chloroplasts and oxygen to exit. Moving on, the upper epidermis is a protective layer that covers the leaf's surface. It's usually transparent, letting light pass through to the chloroplast-rich layers beneath while providing a barrier against physical damage and water loss. Understanding these structures helps us appreciate how leaves are optimized for their role in photosynthesis and overall plant health. Let's take a closer look at the spectral information related to vegetation. As you can see, vegetation reflects visible green light more than red light, which is a key point because it helps us distinguish healthy green plants from other surfaces. The red reflectance is relatively low in healthy vegetation, indicating that leaves absorb red light efficiently for photosynthesis. Moving into the near-infrared, or NIR region, we see a high reflectance. This high NIR reflectance is characteristic of healthy, lush vegetation, as leaves reflect a lot of near-infrared light due to their internal structure. Now, if we consider sunlit soil, its spectral signature differs quite a bit from that of vegetation, generally showing lower reflectance across these wavelengths. The next part of the slide illustrates the impact of leaf area on spectral reflectance. With very low leaf area, the reflectance pattern resembles soil, while with very high leaf area, the vegetation's spectral signature becomes more pronounced. The graphs at the bottom show how reflectance percentage varies across wavelengths, with the y-axis representing reflectance and the x-axis showing wavelength in nanometers. These spectral features are essential because they form the basis for remote sensing techniques used in vegetation analysis. By understanding these patterns, we can assess plant health, biomass, and even differentiate between different types of vegetation. This slide ties into our overall theme of how spectral information helps us interpret and monitor the Earth's surface more effectively. Now, let's talk about spectral information related to vegetation. One of the key points here is that vegetation exhibits high reflectivity in the near-infrared, or NIR, part of the spectrum. This is a really important characteristic because healthy plants tend to reflect a lot of NIR light, which helps us distinguish them from other land cover types. Additionally, it's fascinating that different types of vegetation can be distinguished based on their spectral reflection curves. Essentially, by analyzing how various plants reflect light across different wavelengths, we can identify specific species or vegetation health. This capability is crucial for monitoring ecosystems, agriculture, and land use changes, tying back into our overall theme of remote sensing and environmental assessment. So, understanding these spectral signatures allows us to differentiate vegetation types effectively and support better decision-making in land management and conservation. Let's take a closer look at the spectral information related to vegetation. In the blue region, which spans from 400 to 500 nanometers, we see high absorption levels. This means that vegetation tends to absorb a lot of blue light. Moving to the green region, from 500 to 600 nanometers, there's high reflectance, which is why plants appear green to us. Their leaves reflect more green light. In the red region, between 600 and 700 nanometers, absorption is very high again. That's why red light is strongly absorbed by healthy vegetation, and it plays a key role in vegetation health assessments. Now, in the near-infrared region, from 700 to 1000 nanometers, reflectance becomes very high. This high near-infrared reflectance is characteristic of healthy, vigorous vegetation. Overall, we see low reflectance in the visible region, especially in the red, but a significant increase in the near-infrared. This contrast is crucial because it helps us differentiate between healthy and stressed vegetation in remote sensing applications. So, understanding these spectral properties allows us to analyze plant health and monitor ecosystems effectively. Today, I want to talk about the moisture content of vegetation, which is a crucial factor in remote sensing and GIS applications. As we've seen throughout this lecture, understanding vegetation moisture helps us assess plant health, drought stress, and fire risk. Moisture content essentially refers to how much water is held within plant tissues. This can vary significantly depending on the species, the environment, and the time of year. By analyzing moisture levels, we can gain insights into the current state of ecosystems and make informed decisions for land management. Remote sensing technologies, like satellite imagery, allow us to estimate this moisture content over large areas efficiently. These estimates are vital because they help us predict fire hazards, monitor droughts, and even evaluate agricultural productivity. Connecting this to our overall theme, the ability to accurately measure vegetation moisture content enhances our understanding of the dynamic interactions within ecosystems. It's a key component in sustainable management and environmental monitoring. So, grasping the concept of moisture content isn't just about water in plants. It's about unlocking valuable information for our broader environmental and resource management efforts. When we look at interaction with a water body, one of the key things to notice is the clarity of the water. Clear water allows us to see more deeply, and this visibility is largely due to how water interacts with electromagnetic radiation. In the visible spectrum, water reflects about 5% of the incoming light, which means a small portion bounces off the surface. About 1% is absorbed by the water, so it doesn't make it through, and roughly 90% of the visible light actually transmits through, allowing us to see beneath the surface. Now, when we shift our focus to near-infrared, or NIR, the story changes quite a bit. Water tends to absorb NIR almost completely, meaning very little of this radiation passes through or is reflected. This brings us to an important point about wavelengths. Longer wavelengths, which include the visible and near-infrared regions, are absorbed more by water compared to shorter visible wavelengths. Essentially, the longer the wavelength, the more water is capable of absorbing it. Connecting this to our overall theme, understanding how water interacts with different types of electromagnetic radiation helps us better interpret remote sensing data, assess water quality, and understand underwater environments more accurately. Let's talk about how we interact with water bodies through remote sensing. One of the most distinctive features we see is that water strongly absorbs near-infrared radiation and beyond. This absorption makes water appear very dark or even black in those wavelengths, which actually helps us distinguish water bodies from other land features. In fact, using near-infrared data, we can effectively delineate or outline water bodies with high precision. However, when it comes to assessing water quality, clarity, or biological aspects, we turn to the visible spectrum. Changes in color and clarity are often visible in the visible wavelengths, giving us important clues about what's happening in the water, like sediment levels, algae blooms, or pollution. So, while near-infrared is great for identifying water boundaries, the visible spectrum provides us with valuable information about the health and biological status of the water. This dual approach allows us to use remote sensing effectively, not just to map water bodies, but also to monitor their condition over time, tying into our overall goal of sustainable water management. Let's talk about interaction with water bodies. You might notice that water and vegetation can look somewhat similar when viewed in visible wavelengths, which can sometimes make them tricky to distinguish. However, the key point here is that in the infrared spectrum, they are almost always separable. This difference is incredibly useful in remote sensing because it allows us to accurately identify water bodies versus vegetation, even when they appear similar in visible light. Understanding these spectral differences helps us improve our analysis and interpretation of the landscape, which fits into our overall goal of better understanding Earth's surface features through remote sensing. Today, I'll be talking about our interaction with soil, specifically how soils appear to us. Soils typically look brown because of how they reflect and absorb different wavelengths of light. The reflection happens mainly in the green and red parts of the spectrum, which is why we see that rich brown color. At the same time, soils tend to absorb blue light, which influences their overall appearance. Understanding this interaction is really important in remote sensing and GIS because it helps us interpret how soils behave and how they can be mapped or analyzed from a distance. This knowledge connects directly to the broader theme of how we use remote sensing technology to understand our environment better. Let's talk about our interaction with soil now. When we look at the spectral response, you'll notice that inorganic materials, like soil, have a distinct signature compared to vegetation types. This difference is really important because it helps us identify and differentiate between various ground covers in remote sensing data. The spectral response for soil is typically characterized by certain reflectance patterns that set it apart from the more complex signals we see from vegetation. Recognizing these differences allows us to improve the accuracy of land cover classification and better understand the landscape. So, understanding how soil interacts with light is a key piece of the bigger picture in remote sensing and environmental monitoring. Let's talk about concrete first. As you can see, light-colored and bright concrete has a higher percentage of reflectance compared to dark asphalt. This means it reflects more sunlight, which can influence surface temperature and energy absorption. Now, when we look at soil interaction, it's interesting to note that there are considerably fewer peak and valley variations in reflectance. In other words, soil tends to have a more gradual and steady reflectance pattern, unlike some other surfaces with more complex fluctuations. Factors that influence soil reflectance don't operate over very specific spectral bands. Instead, they tend to affect broader ranges, making it a bit more predictable to analyze. Finally, as wavelengths increase, we see a gradual rise in reflectance. So the reflectance doesn't just jump suddenly. It slowly increases as we move to longer wavelengths, which is an important aspect when interpreting remote sensing data. All of these points tie back to the overall theme of understanding how different surfaces and materials interact with light, which is crucial for accurate remote sensing analysis. When we talk about how soil interacts with light, there are 5 key characteristics to consider that really influence its reflectance properties. First, moisture content. How wet or dry the soil is can dramatically change how it reflects light. Wet soil tends to absorb more, making it appear darker, while dry soil reflects more light. Next is organic matter, which includes decomposed plant and animal material. Higher organic content typically darkens the soil and affects its reflectance as well. Then, we have soil texture, meaning the size distribution of soil particles like sand, silt, and clay. This influences how light is scattered across the surface. Surface roughness is another important factor. A rougher surface scatters light in different directions, affecting the reflectance, while a smoother surface tends to reflect more uniformly. And finally, iron oxide, which is responsible for the reddish and other earthy tones in soil, also plays a significant role in how soil reflects light. Now, within the electromagnetic spectrum, especially in the near-infrared region, water and hydroxyl groups in soil absorb specific wavelengths, like around 0.9, 1.4, 1.9, 2.2, and 2.7 micrometers. These absorption features are crucial for remote sensing because they help us identify soil moisture and composition. So, understanding these 5 characteristics helps us interpret soil reflectance more accurately, which is essential for applications like land use management, agriculture, and environmental monitoring. All these factors together influence how soils appear in remote sensing images and how we can analyze them effectively. When we talk about the reflectivity of surfaces, or their albedo, we're essentially looking at how much sunlight they reflect back into space. For example, fresh, dry snow has a very high reflectivity, ranging from about 70 to 90%. That means it reflects most of the sunlight that hits it, which is why snow can help keep areas cooler. As snow gets older and starts melting, its reflectivity drops to roughly 35 to 65%, because the surface becomes less pristine and more absorption occurs. Moving to deserts, sand has a lower reflectivity, generally between 25 and 40%. Dry vegetation and grass also reflect sunlight, but to a lesser degree, around 15 to 30%. This lower reflectivity means they absorb more heat, influencing local temperatures. When we look at forests, deciduous and coniferous types, their reflectivity is quite low, roughly 15 to 25% for deciduous and even lower for coniferous forests, about 10 to 15%. This absorption contributes to warming in forested areas. The ocean surface is particularly interesting because its reflectivity varies significantly depending on the sun's position. When the sun is low, the ocean can reflect between 10 and 70% of sunlight, but when the sun is high, the reflectivity drops to less than 10%. This variability impacts how much solar energy is absorbed by the oceans, affecting climate and weather patterns. Finally, bare soil tends to have a reflectivity of about 10 to 25%, so it absorbs a lot of sunlight. Understanding these differences helps us grasp how various surfaces influence Earth's energy balance and climate. Let's wrap up by discussing the spectral signature, which really helps us understand how different surfaces appear in remote sensing images. First, why does water look darkish blue? Well, water absorbs most of the longer wavelengths like red and yellow, but it reflects and scatters shorter wavelengths, especially blue. That's why water bodies often appear blue or darkish blue, especially when they're deep. Next, vegetation appears greenish because chlorophyll, the pigment that plants use for photosynthesis, strongly absorbs red and blue light but reflects green light. That reflected green light is what our eyes see, giving plants their characteristic color. And finally, sand looks reddish-yellow because it contains minerals and iron oxides that reflect those warm colors. The composition of the surface materials directly influences the spectral signatures we observe. All these differences are crucial because they let us identify and analyze various land cover types from afar, connecting directly to the core idea of remote sensing, that each surface has a unique spectral fingerprint. Understanding these signatures helps us interpret images more accurately and make informed decisions based on what we see from a distance.